Welcome everybody. We're talking about the mutations. I'd like to spend some time to do some coding in Python and just kind of get you ready for the lab that's going to be coming up today. In our lab, we have some coding that's going to be, you're going to be writing some code, you're actually going to be reading some code and trying to figure out how you can fix it. It's actually kind of a fun little lab, I think, but who knows. Before we get started, though, let me just take you back to the GitHub repository that we have here, the class docs. If I can find my way there with all this stuff that's open on my screen, and show you really what I expect you to do with how you pull over your. Now, if you've seen this before, then I do apologize, but I'd like to take a moment here just to show you how to pull over your latest material from your class docs repository. Oops. So what I'm doing now is in my repository here, I have, this is how I organize my files. I have Spring, then I have CS300, and then I have class docs. And so this is where I keep the class docs for class. And so you can see these are the classes that we've had. And if I just go ahead and type in git pull, then really everything should be, everything should show up on your screen. And so in our labs here, or in our not our lab, but our lab will be, you'll see that later on. But in our lessons, you should have, for instance, the 06, 15th of March. And that's, that should be there. Does everybody see that part on their thing? Could do, if you don't see that, then it means that you're probably typing in you're typing in your command in the wrong place. And what I mean by that is, for instance, if you are outside of your class docs, like this is where my class docs is, but if you are outside of class docs, like here, for instance, and you're typing in git pull, it's probably not going to work. So I'm only saying this because I've had a number of mails over the, I think three mails over the weekend asking how do I get to my class docs repository. And so it's this way here. So you actually have to be inside class docs, and then you type in git pull there, and everything should come over. Now, because I've already done this, I'm already up to date, and so there's nothing that I can really change out. And so there's, but on your machine though, you'll probably see like a bunch of stuff that just shows up here where it's, it's going to be all, the different things that have actually shown up. So let me just take you into the thing and show you what we have in store for today. There's a couple of things I wanted to show you, and that is that I have changed the Docker file. And so the Docker file that you have from our the first time we saw Docker, that file is obsolete now. That means I've made a change to it. I've only changed one line, in fact. But now I've added this line here that's pip install Biopython. And so what that means is that you can now run Biopython type software in your container. Now, Biopython is really what we're going to be doing in today's lab. We're going to be hitting it basically throughout the semester, I think. But it does a lot of really amazing things in bioinformatics. For instance, it can help you to organize some of your data. It can help you to translate and transcribe. Well, you can transcribe DNA to RNA, which we're going to be doing in a moment. And you can translate that into protein. And so it's like we special code to make these things happen, but rather the biology has been superimposed into the computer in this library, and so that when you run this, you're able to, to use code that will help you to do your manipulations in bioinformatics. One thing, for instance, that I used Biopython for was to organize my data files, and that means that when I was downloading DNA from a repository, I was able to do that automatically from the code. We won't do that today, but we'll do that this semester, I think in a couple of weeks, where we actually use Biopython to reach out and pull over data that we can process like on the fly like that. And it makes everything so much easier. Rather than having to download the data yourself, format the data with a text editor, move things around, do this, and manipulate it, and then wrangle it, and then get it into position so that you can actually send it into your analysis. Well, in a couple of lines of code, Biopython, which is really, really handy. It's really, really handy. Anyhow, so let me just go ahead and show you something before we get started. What I want you to do is you'll need to run, or actually you'll need to build your new Docker container here. And so by that, what you do is on this machine, this is a Mac machine here, so it's basically Mac and Linux, but it's a Mac. I'm going to be running this I have to run my build thing here because I've already, I have to rebuild it from the ground up because it's got a new. But I type in build macOS sh. Don't forget that this command here, sh, if you can all see that where I'm typing, this sh, that means it's how you run these script files. And there's other ways of running them, but I'll run them this way because it's easier that way. Now, when you type in this command here, sh build Linux or Windows or whatever you're using, you're going to see a slightly different outcome here. This is the process of building your container. And by that, what that means is it's going to go through the original container that you already have, and it's going to determine that that container is no longer the same container which is being requested to be built. That means that it's going to be saying, oh, well, here's the library that you don't have, so we better rebuild this thing. And so these lines of codes here, checking and building, or downloading the software and then building that container. So you want to do that. Otherwise, if you don't rebuild your container from last week, then you will not have the Biopython libraries installed, which is going to make things difficult for today. Okay, so once you've done that, I'll just let that thing turn for a while. Once you've done that, run it, sh run. And here, you'll notice that in green, it says you may be asked for your password. That's not a security thing. That's just asking you for your password so that when you have finished writing your files, actually when you're in your container rather, when you write a file in your container, that file belongs to someone called root, which is like the super user on your computer. And that's how you run your containers. You are root on your computer. That means you have all the privileges that you can possibly have on a computer. And so when you leave that container, that file that you wrote is still reserved under the name root. So that means that when you're back to your regular prompt where you've left your container and you're back outside of the container again, it means that those files are locked out to you. You can't get to them. It's like they belong to root and not to you. And so by typing your password here, what this is doing, I'll just tell you, just so there's no alarm. But it's running this command down here called chown, which really just changes the ownership of the file. So it goes from root and it goes back to you. That means now you have privilege to write and move that file, or to erase it, or to edit it, or do whatever you want with it. And so that's asking you for your password. And so don't worry about that. If it does ask you for your password, just enter in your system password. It's not your email password, it's your system password on your machine that you're working with, and that should be okay. I think that on a Windows machine, it doesn't, I don't think you need your password, but on a Linux machine and a Mac machine, I think that you might. So it should work. And so anyway, I'm just saying this so that there's no cause for alarm. If you find that your machine is not, or if you find that it's like asking you for a password, you're like, why is it coming through? I wanted to show you something else before I get any further, and that is that there's a piece of software that's in your thing called bindna. This is actually kind of an interesting little experiment, and I use this to discuss with some computer scientists about how bioinformatics and computer science were actually very similar. And I'm not going to show you the slides for this whole thing. I mean, we can save that for another time. But I use this piece of code here called bindna. And what this thing does is it allows you to, it's a toy, basically. It's a toy. But what it does is it converts DNA to binary and then binary to DNA. I mean, it's kind of a random type of program here. But I did this to prove a point, and that is that the talk that I was giving was about how it was trying to justify how DNA and binary code and all those things were kind of central pieces to bioinformatics. At the time, everyone thought that it was like, bioinformatics was just biology, and you're basically growing stuff in petri dishes and working in a wet lab, and every now and then you step away and you write a piece of code that helps you to figure something out. And that really wasn't the nature of, that's still not the nature of what bioinformatics is. Bioinformatics is taking pieces of data from biology and then crunching them in computers and using them to make models and to do all kinds of amazing things. And so the question came up, like, how can you work with DNA with a computer, because DNA comes from cells and computers don't have anything biological about them. So here's this program that I wrote, which is basically saying that you can actually convert DNA to binary and then binary back to DNA, and so they are equivalent. And so how you can work with this is this. I'll just show you the files I have. There's this regular piece of DNA. which is just regular code, DNA. And then so what I can do is I'm going to convert that to my, I'll convert that by typing my DNA thing here, and I want to say that my option or my parameter is binary. So basically I have to say the file name, then I have if it's DNA, it's like it's a piece of, I put that code or that file here. I want to do with it, which is bin, and what it does is it says, okay, I've taken your input string and I've converted it into binary. And so this is actually a very important piece, because you might find that as you're working with your research, and I mean all the things all the things I tell you now are really for your senior, well, not your senior thesis, your project in this class. I was going to say your senior thesis project, but I don't mean that at all. But your project for this class. And so you might find that it might be necessary to convert DNA into binary. And so now you have some means of doing that. And you can always use this code, by the way, if you wanted to kind of say, well, actually, bioinformatics and computer science, I mean, and biology, they're all really connected. And in fact, if you have DNA, you have binary. If you have binary, you have DNA. And so you can connect everything together. But how this works is this. Really what you have is, if you have an A in your piece of code, it superimposes a 0, 0. That's where this 0, 0 over here came from. If you have a T, for instance, it takes the T that it finds over here, and it superimposes or it converts T into 11. And these are all just, I mean, codes that, I mean, they don't have to be this code at all. You can change the binary code. A could be not 0, 0, but it could be 0, 1 if you wanted to, or whatever it may be. But still, that's something you can play with. But it does make a point that you can change DNA from one thing to another. Now the next thing is, I'll show you how you can go in the reverse have the reverse operation here. That if I have, for instance, if I have binary, a binary file which looks like this, I can convert that back into DNA looking like this. And so I'm saying this because as you go through your careers in bioinformatics, there's going to be somebody who's going to tell you, you know what, DNA and binary, they're totally different. I mean, how can you possibly work with one using the other? Well, actually, though, if you think about it, we use A's, T's, G's, and C's, and our computers uses zeros and ones. And so really, it's a kind of it's a similar simplistic alphabet that all of our code runs in. And so you can use this as a kind of a starting point to discuss how bioinformatics actually does encompass biology as well as it encompasses computer science, and it all kind of comes together. But this is a toy, though it doesn't do anything else. I provide the code for you to look at here, so you can kind of get an idea about how it works. We are going to be spending some time talking about the code, and I'll just kind of like take you through some of the pieces that are going to be important. In this particular code, for instance, when you first run it, everything begins at the very, very bottom. You'll notice that all of my codes actually begin at the very, very bottom like this. And so the code that we do today could be rewritten so that you have some piece of code down here that actually kind of orchestrates or runs the code from the command line. What this is doing here is it says, I'm looking for, actually it's not 3, but it's 2 parameters. The third parameter is the file name. But it says that when you run this at the bash, look for 3 things. One of those 3 things is going to be the and the other 2 things will be the parameters. This is going to be the file name that we run, and this is going to be over here what we're doing with that file name. Are we making if this is a file name which is the dna.txt file, this over here is going to be the bin parameter, and so that's going to be kind of telling you what to do. But what I'm saying though is that if you go to this function here called begin, if I move up wherever that is, right here, this is the driver or the main of my code. And so as we go through our coding operations today, you'll notice that much of the stuff that it's the same mechanism that I use, where I always have some kind of central driving function, and everything kind of like comes from that kind of orchestrates all the pieces that come together to make the program run. Let me go ahead and just get started here. I'm thinking that by now, hopefully everyone's build has finished. Hopefully you've been building your container, and so hopefully that's all done. And so what I thought I would do now is I'll leave you to look at this code if you'd like to see it. But I'm going to go to my prompt here, and hopefully you guys can all see this. I'm looking at the board here because sometimes hopefully it's clear enough to be able to see. Maybe I'll make this a bit bigger. And we're going to start just doing some regular coding. And I thought what we would do today is we'll write a piece of code that will accept a piece of DNA. And just like this program here, it's not going to convert the DNA to binary, but rather it's going to convert the DNA to protein and RNA using Biopython. And so let's go ahead and get started. Excuse me. What I'm going to do is I'll leave my code here, and so you can just have this if you want. I'll push this out to the rest to the class here, so you get this. I'll be writing up in Vim, but actually in any editor you want, and I'll call this dogma, I guess. Dogma. And so what this is going to be doing is, as you remember, this is my editor. As you remember, the dogma is the central dogma of biology is saying that take your piece of DNA to RNA and then convert that into protein. So we're not going to do that actually, like we're not going to write the code ourselves, but rather we're going to be using a piece of code that's going to do that work for us. Okay, so let me just save this here. I'll just save this file here. I want everyone here just to try one thing for me, and that is get out of your editor or go back to the container where you're actually running, that you've actually run here, your container, the Docker container. You should see something like root, something like this. I'm not really sure what all this. I think that this number over here is like the serial number to my container. It's going to be different on your machine, but it's something root at something like this. Now, what I'm going to do is I want to make sure that my Biopython really is installed. And a simple trick that you can do to determine that is you type in, for instance, import. Oops. Hopefully everyone can see this. You type in import bio with a capital B, and you press enter. Okay. Now, if you get an error at this point, it means that it hasn't been installed properly. That means that you're not running your container. You might want to make sure that you have that you actually typed in sh run underscore Mac OS or Linux or Windows to make sure that you're inside your container. Now the next thing you want to do is you can see the version is of your software by typing bio. You do print, and then inside your parentheses you have bio, and this looks kind of crazy, but it's underscore version underscore, which I think is probably one of the most insane types of software code I've ever seen in my life. I mean, what does that mean? But Python seems to love these underscores, and so anyway, there you go. You should see a number, and on my machine it's 178, and I'm guessing that it's probably going to be the same number that you have on yours. Does everyone, you have that? And do you have that too? You have the same number, perhaps?
Oh yeah.
Perfect. This number, it could mean that it doesn't really matter if it doesn't have the number, but I'm sure that it will be the same number. But import bio does not work. It means that something terrible has happened, that you're not in your container. Okay, I'm gonna jump out of Python here, but what I've actually done here though is I've been able to get and actually write some code line by line without having to first write a program, which is actually really kind of handy now and then. So let's get back into the code that I started with here, and that's actually, where did I write my code here? Dogma. And I'm going to go ahead and just start by defining my libraries. So we need to import the library. Now, you can use Vim if you like. When I first saw Vim, I absolutely hated it. I thought this was like one of the most impersonal and user-unfriendly libraries I ever saw. But you can use this. But otherwise, you can use your regular any editor you want to use, as long as you save that. As long as you save your text, or sorry, your source code, in a place where you can access it from your repository. So in other words, to your source repository, and then putting everything there. By the way, let me just say something. Typically, you want to leave all your, today we will because it's fine, but at the end of this, you want to move that file out of your class docs and put it into another directory where you can hold on to it, because if something happened where you erased your class docs and pulled over the next class docs, you lose your own files. So you want to save those files someplace I mean, because we've already run the container and we're inside class docs, then you may as well just keep it there. But then just remember that at the end, move those files out so that you have them someplace where they're not in class docs. Okay, so anyway, we have this import thing. So now that's going to import the, actually it's not this in the library here, but this is the Bioinformatics library. So by the way, when I'm writing my code here, this pound sign that you see right there, hopefully you can see this clearly. If it's blurry, I do apologize. I don't know how I can make this any more clear. But anyway, you want to have this pound sign here as your little comment here. That means that anything that's behind this pound sign, like this statement import Biopython library, that's going to be ignored. Now the next thing you want to do is you want to type in the next library, which is bio.seek with a capital S import seek. Oops. Now, this is my other library. So these are the libraries that I'm going to be using from Biopython. That means that I want Biopython to load this bio library. And a library is basically like a collection of code that I can just use later. And then I have, in this book here called Seek, this other library here, I want to bring out this specific chapter, part of the code. I don't want to bring out everything because maybe everything is too much, but I just need that. So I have that. And so the next thing I want to do is I'm going to type in, I'll just put in a function here, main. And this is going to be to run the program. So in other words, I'm going to be saying when this program first runs, saying, okay, load these libraries. Now, once you hit this line here, find this function today, but find this function called main and then run it. That's all it is. It's a call to a function. So I do apologize if I'm going slow and you've had experience with Python before. If you have not, hopefully this is beneficial, and that should be, I mean, it should help. Okay, now what I'm going to do is I'm first of all going to, I should probably put in something else here just to make it, I should probably put in I should define my function here. So I'm going to go above and I'm going to define my function, and you do that by saying def for definition, and I'm going to say my function is called main. Now, one thing that I find that I forget about seemingly all the time is putting in notation like this colon here. That colon basically says this is the beginning of a function, and everything that follows this function is going to be the code that is run when that function is called. One thing I also do, which is, you don't have to do this at all, it's purely personal. I always put, for instance, end main. Now, let me just say something here. The way that Python works is a little bit different from how Java works. Java has curly braces around code blocks. So, for instance, you run something, and the stuff that's inside the curly braces is the stuff that's run in Java. But in Python, it doesn't work that way. In fact, in Java or in Python, it's the indentations. So, for instance, every time you indent something, that represents with the same number of indents is your coding block. And so what I do is I put this end main at the end here to help me to remember, and I do forget things, but help me to remember where the end of my code block is. When I first learned coding, I learned in Java, and so I still have this Java that washes over everything I'm thinking, so I do apologize for that, but this is a good fix. Next thing I'm going to do is I'm going to add a docstring. This is called kind of like a little piece of information to tell me what it is. You have 3 quotes followed by a space and 3 quotes, and inside that space I'm going to put the driver function of the program. And so what this is, kind of like what this thing is. It's like your identifier. When you're dissecting your programs later on, when you're trying to make your programs work, if something terrible happens and you're trying to diagnose what all your little functions are doing in your program, and then one of them is not working, this will help you to remember what each of those functions is supposed to do. So maybe I should be more specific and say driver function of program. I'll say this, I'll just say demonstrates the central dogma, of bio in Biopython. Something. It's just something for me. The compiler doesn't read it. It doesn't read it. Now I'm going to save this because it's there. I hope that everything's okay. Like I said, I will make this code available to everyone here so that you can have this, so that if your code just is not behaving, then I hope that at the end of class you can look at this code and look at your own code and find out where the problems were. So first of all, I'm going to put a print statement here, and I'll put something like, welcome to central dogma of bio demo. Something, I'm just putting it like that, just so that now the user is going to see this part. I should put a the in here. But the user is now going to see this. Let me just show you something that's actually kind of interesting. That is that I'll go ahead and save this. And we'll come back to this in a moment here. Just wait, give me a moment here. I'm going to save this, and then I'm going to quit it. And if I go back, you'll see that my file is right here, dogma. Now, if I go ahead and run this file, I can type in Python 3 followed by dogma, push enter. Whoops, I made a mistake here. I did this on purpose, actually, but when you run your code, this is how you read errors in Python. Now, when you first see these things, it's almost like an allergic reaction. You're thinking, oh my God, what do I do here? But actually, though, spend some time looking at this line here that says syntax error, invalid syntax. This is saying that on this line here, and Python is smart, it kind of points things out. It says that there is a problem here, and that is that I'm reading this line and I can't make out this word here. That's where this caret is. So I can see what the problem is. I've misspelled something. It should be import with a T rather than just import. So I can go back and change that. And I'll show you, if I go down here, I add this, and it's set. I've just put a T on the end of this. I save it, and now I can go back and run it. And you'll see that all the program now does is when I run this program like this, Python 3 dogma, all it does is it prints up this string of text to the screen. That means it's loaded the libraries, but you see nothing. It doesn't tell you anything about that at all. This says libraries are loaded. If the libraries did not load, then you'd have some kind of an error like this. You'd have an error, something. But because the library is loaded, that means that everything is fine. It's just, it moves on to the next piece of the code. Okay, so let's go back to this thing here. Now, remember we're running this part of we're building out this function here called main. So the next thing I'm going to do is I'm going to put in, actually I'll tell you something else that's kind of cool. Print, this is what I tend to do. You don't have to do this if you don't want to. Actually, tell you what I'll do, I'll put some tabs in here. I'll put Bioython version. This is another print statement here that just looks like this. Biopython version. Everyone see that? Nothing unusual there. And what I'm doing is I have this comma here, and that says I'm now going to amend my string, or I'm going to add something to my string. So I'm going to, and when I print that out, I'll have like one giant string, which is actually going to be made up of smaller parts. And so what I'm going to do is I'm going to have the same piece of code that you and I typed in earlier, which is this. There we go. And that's it. Notice, by the way, that when you're typing in Python, there's no semicolon at the end of each line. That's a Java thing. I'm speaking to the to the people who haven't seen Python code up close before like this, but you don't have those things at the end, and if you do, it'll confuse things. I wish that some of these programs would just be. I wish that all coding were like very similar in some cases, like where you either all languages had them or all languages didn't have them. It would be because it would be much easier for me to teach. Okay, I'm going to go ahead and get back to my prompt. I'll just show you what this thing does, just so you have an idea. I've saved this work. If I run this, you'll notice that now it says, I've added some tabs here. That's why there's a space here. But you're saying, you'll notice that now it just says, I have this tag there. Now, I do this not just to make more work for myself, but sometimes when I'm writing a report and I've used Biopython, I record the output of my code. And I want to have that version in the output so that if, and it happens all the time in computer science, but if the libraries change, where somebody changes something, where the code no longer works the way it did when I first wrote this code, then I can see from the output in my manual or the paper that I'm writing, I can see that the version that this thing was supposed to run at was 1.78, and I see now that we're at version 2, something has changed, it's not going to run. And so that gives me an idea about, it's not the code's fault, but it's the library that's changed. And so it helps me to go back and fix things. Okay, so the next thing we're going to be doing now is I'm going to be defining I'll make a little comment for myself, define the DNA sequences. Okay, so my first sequence is, I'll just call this my seq A, or my DNA, I can never call it something easier, my DNA sequence A, something like that. this is just a variable. Now, I'm not doing anything amazing here. This word, my DNA seek A, is a variable. It doesn't mean anything other than that. It's basically a memory of the computer that holds onto a piece of information. And the information that I'm going to apply to this is if I put in seek parentheses quote, I'm going to put inside a piece of DNA. I'll just put in AGT, I don't know, ACA, oops, GTA, something like that. It's just a piece of DNA code. Now, I need to do this again, so I'll call this my DNA seek B is equal to seek. I think you guys can kind of see where I'm going with this, but I'd like to be able to kind of make a program here that eventually, that converts everything and then eventually does some kind of a, I'm going to make these two different here, but basically it does a kind of a comparison. I want to compare my sequences. After all, that is the central piece in bioinformatics, to compare things. How different is this sequence from that sequence? How different is this organism from that organism? Is this the same virus? How do we know? How we can check? We can convert. Well, we can compare the DNA. So I've just defined my DNA sequences, and now I'm going to do another thing here. I'm going to say, okay, I'm going to make a print statement here. Print the sequences. Oops, I'm making a mistake here. I'll call my first sequence is going to be this, sequences. I'll say my sequences. I'll put a tab there just because, oops, make it easier. And again, see what I'm doing down here? This is exactly the same magic that I used up here. It looks different, but I can assure you it's exactly the same, where I have a string, which is surrounded by these quotes. And here's another quote over here. And then I have a comma. Everyone can see this comma. I have a comma down here too. And that comma then says, okay, thing, whatever follows me here, on to the rest of this sequence, the rest of this string. So that's my first thing. And now what I'm going to do is I'm going to do this again. I'm going to make this into, I'll have sequence B. And because I have sequence B in my print statement, I have to have my sequence B down here. So in other words, I have to change these variables to reflect the output of the string. So what does this actually do now? Well, let's just go ahead and run this. And I think that if I run this, you'll see, and I'll come back to the code in a second, just give me a moment. But if I go ahead and exit this, and I run this again, you'll see now that I have, it says welcome to the thing. We've seen that before, the sequences. So these are sequences which I have actually hard-coded into my thing. So now it's saying these are some DNA sequences. We're now going to put these sequences out onto them. We're going to just print them out as input. I'm not going to do anything more than that. So let's get back to this. So what we have now is we're going to run with, well, let's do some fun stuff first of all. Before we do let's see, where can let's convert this stuff here. I'm trying to find my notes here to kind of get the best. Okay, well, translate this stuff here. So I'll tell you what I'll do. In fact, I'm going to go over here for a second here. Let me just get my cheat sheet up just so I have it. Okay. Okay. So what we're going to do now is I want to go ahead and let's just translate our DNA here. So translate. We could transcribe and translate. I think we'll do the translate first, just because I think we can jump to that. Actually, do I have transcribe in my? So the thing about this is, I'll just tell you that when you're working with, well, actually, before we do that, let's do a complement. Let me add some other stuff here too. Let's do this. We're going to do a complement of sequences. Okay, so these are like my little areas. This is how I know. This is how I'm going to be thinking through my code here. So I'm going to write the complement of my sequences here, and so we're going to use a piece of Biopython code, which is just called a complement. So we'll say that, for instance, of my DNA seek A is equal to. Now, how we do this is I just happen. I'll just copy this out here, so I'm lazy. But I have code that looks like this, and I have dot complement. Okay. So basically, that's it. That is the code that you do. Now, what is the complement of a piece of DNA? it's where every A is written out as a T, and every T is written out as an A. G's and C's and all that are basically, it's like everything is you find the opposite, it's the opposite strand. If you're working with a sense strand, you have the anti-sense strand. Now, let me go ahead and just do this again. I just have to edit this. I just copy this line, FB. So what I'm doing now is I'm saying, okay, this is a new variable. It's a new bookmark, if you will, to a place in memory that holds a string, which is going to be created by this function here, complement, which is going to be acting on this function, or this string here. So in other words, all it's really doing is it's just picking up a piece of code, or pick up a piece of string here, and then it's just going into the libraries of Biopython and doing some stuff with it. So let me put my print statement here. The comp of sequence A is, and again, remember what we're putting after this? We have this comma again. And I'm going to say, I want to show what's in memory from here. And so this, if I go ahead and just dump this in here, I have this comp of my DNA seq A. One thing I'll notice, I'll draw your attention to, is that as you are typing in these things, as you're creating your particular variables that you're working with, please do keep in mind that you want to find variables which are actually easy to work with. In other words, you do not want to have variables which are like really, really complicated, which when you look at them, it means nothing to you. You want to have a variable which, when you first see this thing, it has some meaning. So for instance here, I know what this variable is without having to print this thing out. It's the complement of my sequence. It has some meaning to me. Let me go ahead and just copy out the whole thing again. And I'll do this complement of sequence B. We're just doing two different sequences now. And I'm going to go ahead and I'll save it. So this is what your code should look like. Complements. So I'm creating a new variable, which is being created by this function complement, which is working with this string that I have here. That's just how Python does it. You have the string, and because it's an object-oriented programming language, you have this dot over here, which means apply this string to this function, and then that function will return something, which is then going to be saved to this variable here. The same thing happens with B. Let me just go ahead and run this and just see what happens now. Hopefully it will work. And it does. So for instance, here we have, in fact, I should do some formatting here where I indent everything. But you'll see that my DNA seq is over here, which is the original one. And then you'll see that the complement is going to be this piece of code over here. So where you have A's up here, you now have T's down here. And where you have G's, you have C's. And so if I wanted to actually write a piece of code myself to do this work, I mean, it can be done. You can all do this. But the thing is, though, that you have to do that. And so this is code that's already built into Biopython, which actually gives you that that complement by yourself. It's like you don't have to do anything more than that. Now, let's go ahead and do something else here. And that is that supposing we wanted to, let's go back to my coding here. I want to see the reverse complement here. What is the reverse complement? Well, the reverse complement, as you remember, is, let me go ahead and just copy this. By the way, does anyone have any questions? I don't want to just keep on charging through this. If you guys have questions, I mean, just stop me and ask. If you have questions, I mean, just let me know. So we have the complement. Now, remember that when we talked about DNA, you have the directionality of DNA, where you have the 5' to 3' direction of DNA. That signifies that the DNA is being read, or that the genes are being read out in the 5' to 3' direction, or rather, DNA is being constructed in the 5' to 3' direction. They're the same. And so when you have one DNA over, if I get my hand on the camera here, you have one side of the DNA over here, you have another side of the DNA that's going to go in the opposite direction. So if my thumb is the 3' direction and my little finger is the 5', then you can see that the direction here is going from the floor to the ceiling. But on the other side of my sequence, I have the direction is going to be upside down. So my thumb again is the 3', so that's going to be going down. And so you have these two opposite-ended pieces of DNA that are coming together in the same string. And so you might want to just figure out, well, what is the reverse complement of my sequence? In other words, what is the opposite side of the string, but upside down, that I can use? And for this, I'm just going to copy out some of this stuff over here, just because I'm lazy. And I'm going to paste it down here. I'm using Vim to copy things around. You don't see all the hands or the things I'm doing, but if you're interested in learning more about how to use Vim, I can help you with that. But I'm going to just change my variables here. Remember that I have now, I have my complements and I have my reverse complements. I'll call this rev comp down here, rev comp. Again, I'm using I'm trying to use a variable name which means something to me. So to do that, I just need to go back and say, okay, well, here's my sequence over here. And what I'm going to do is I'm going to just take I don't have to actually do any other steps, but I'm just going to say I just type in a command right here, which is reverse dot complement. Reverse complement. Oops, actually not dot, it's underscore, sorry. Reverse complement. That's it. And that's good enough for sequence A. And for sequence B, it should be the same, R-E-V-E-R, reverse comp of my sequence B. So I'm hoping that that's all it's going to take. And over here, I need to go back and change, since I have over here rev comp, I need to go back and fix this line here so that the variable now is being, the new variable is being reflected. And, oh, you know what, I don't need to change this here, sorry, hang on guys, I was in the wrong place. There we go. Your code should look like this. Hopefully that'll do it. Okay, so that should do it. And so if I go ahead and save this and I run this, there we go. So actually let me go back and fix something before I do that. Let me go back and change my print statement here. Rev comp. In fact, I'm going to put some tabs in here just to make things a little bit cleaner, perhaps. And a space. If you put a /n and /t, the /n means drop a line. The /t means give you a tab. So you'll see that each of these groups now, this over here, and when you look at this on the screen, it's gibberish, but when it prints out, though, this part over here says drop a line and then indent this. Over here, we're not dropping a line because the print automatically does that, but I want an extra line to drop. Over here, again, I have my tab, and you'll see how that looks when I run this. So here we go. So I have, for instance, my first sequence is this, and then my reverse sequence for sequence A is TAC, and that does kind of, it does jive. When you look at this, it takes some time to kind of figure out how this is correct. But remember, though, that here we have T, which is up here. And then if you start, that's for your A sequence. And then on my reverse complement, I'm starting at the very end, and I'm working my way back. So I have the A from the beginning of my sequence A is A. And so the end of my rev sequence is going to be T. The second sequence on my DNA is going to be G. So the second to the last is C. The next one's going to be T over here, and then the second or the third to the last is going to be A. And so it's the sequence which is backwards. And so that's actually kind of cool. And so we can do all that. All right, so let me think what else we can do here, which is actually kind of cool. I wanted to actually get into some of the more heavy stuff here. Let's get some protein out there. I'm just looking to make sure my notes are okay here. Actually, I'll tell you what, why don't we get some RNA here? That's another thing about the central dogma of biology. And so I'm going to go back and I'm going to run this. And now let's subverse complements. Let's not do translate just yet. We still have to do transcribe. And remember, transcribe is where you're going from DNA to RNA. So we're going to convert everything over. So now what I'm going to do is I'll just copy over these same lines of code up here just to have them. And I'll go down to the bottom, and then I'll paste them in here, and then I'll just edit them the way they are. So what I'm going to say here is not comp, but I'll say RNA of my DNA sequence A, and I'll say RNA of my sequence. Now, what we need to do over here is we don't need to have complement anymore because that's not going to give us the right answer. That's going to give us the opposite thing here. But what we need to do is we need to type in something called, if we're working with transcribing, can anybody guess what the command might be to transcribe? Transcribe. It's just transcribed. It's like they don't want to make it too crazy here. Kind of simple here, but it's basically this transcribe, and I think this is all that really takes. I think that transcribe will do it. So I'm going to just type in the other one here. There's two ways of doing this, and I'm hoping this way will work on this particular setup here. And I need to go back over here and change this RNA. So basically what I've done now is I've changed my, I'm making a new variable called RNA of my DNA sequence. And RNA, and now I've changed, I have this variable here, and so I have to put that variable down in my print statement so that I know what's going on. Then I have this over here, another new variable, and that variable must go over down here too. Now, let me just go ahead and save this. We'll come back to it in a second, everybody. There we go. There we go. Transcribed. Now, you could write this code again yourself, but it's nice having libraries. Now, this is probably, you're probably thinking, this is incredibly simple. Why would I care about this? Well, this is to prove to you that Biopython does have many things that you can use. I mean, this is just one of them. But imagine now something that's much more complicated. But I want to kind of go into this kind of gradually here so that you have an idea that all this stuff is available to you. You just have to find it. There's a bunch of other commands here that you'll use for your own work, which will make everything much, much more easy. Now, I know this is RNA. Now, go back to sequence A here, up here. Now, remember RNA has U's in place of T's. DNA has T. DNA has T. But RNA has U. So you can see that the DNA sequence is practically the same, except in here you find that there are U's in place of T's. And so you have U's here and U's here. Otherwise, the code is exactly the same. And so that's how you know that RNA is coming through. So so now you know that you have your RNA. All right, good. I hope everyone here is as excited as I am. I'm just absolutely stoked. I think that Biopython is just really, really cool. Now, the next thing we're going to do here is we're going to be doing some translation here. Now, remember what translating is. That's going from it's RNA to protein. But the thing is that we don't have to worry about, actually, the nice thing about this is we don't have to, because it's a computer science tool, we don't have to work only with RNA to transcribe. In fact, we can just give, or to translate, we can just give the code DNA directly and then have it work through. So I'm going to go ahead and copy out this code again. I'm going to just dump it down here, and then I'm going to go ahead and edit this thing here. So I'll just say protein of my DNA sequence. These variables are getting kind of ridiculous, but it's the same here. I'm going to change RNA here, actually I'll put protein here just to make it easy. So I have my protein of sequence A is this. Now I need to change this over here, and what is this going to be? Well, this is going to be my protein. So everyone see, the reason why I'm going through this actually is to make an important point, and that is that when you just copy and paste code, you must make sure that you go back and reassign the variables or change the variables as necessary. So what I've done is I've created this new, we haven't edited this yet, we'll get to that. But over here though, this is the new variable that I've just created, which is going to be the protein of my DNA sequence. And then I have this variable over here, which is the protein of my DNA sequence B. And what I'm going to be doing is I have to, I take these variables that I've created, and we're going to change this in a second. This is going to be then pushed into this string, with this string over here, and kind of stuck together. And so it's, again, it's another output. And that's all it is. It's just an output. Biopython just does the work, returns a string, and then gives you this thing. Now, if the first thing was transcribe, can anyone guess what the command might be or the function might be that would translate something? Translate. yeah, it's not very it's not very difficult. But actually, that's the reason for that is so that it makes sense to you. So that when you go ahead and sit down and start writing this stuff, it makes sense. So we have translate. So if I go ahead and save this, hopefully I've make sure my variables are all correctly done. If I go ahead and save this and then I run this, you'll see now that I can. Oops, it's not defined. Here we are, another error. So it's important to look at this and find out what's going on here. What this is saying is that some variable that I'm trying to use is not defined. In other words, it's kind of like when you're talking to your buddies and they're saying, hey, Jimmy and I went out the other day and had pizza, it was great. And you're like, who's Jimmy? And he's like, Jimmy. And you're like, who's Jimmy? He's like, Jimmy, you know. And you're like, I'm sorry, name error, name Jimmy not defined. It's that kind of thing. By the way, if you say that, that just seems weird, but you get the point. So what I'm saying is your variable, your computer or Python is talking to this code, and the code's like using Jimmy, and Python's like, what are you talking about? Who is this guy? And so you need to go back and change this. And so what I've done here is I've made a mistake here where I call it prot f. That was just a bad thing here. And so now Python knows who Jimmy is, and it should be able to run, and it's still not defined here because I didn't do something. What did I do here? There's some error, but it should be, it should work. By the way, one nice thing that I like about this is it says on line 48 and 62, 48 I think is where we're working. You can go back and find out on 48, which you can see in your editor someplace, what's going on. So prot of my DNA sequence B, what is this here? So I'll just go ahead and copy this because I'm lazy to see where the error is making a mistake here. I wonder whether that's because of me or whether I made a mistake someplace else. Hopefully I'll run this again. There we go. So that seems to work. So I made a mistake in my variables, and so now Python knows who Jimmy is, or who this variable is. But this is actually a very important piece here. The other stuff, this stuff above here, was trivial. It's not very difficult at all. But this part down here, to actually convert a sequence of DNA into a protein, this is magical. It is magical because the code that's involved in this process is actually quite extensive. This could be probably, I would say, you have to define all the different amino acids. You have to make a parser that goes to the DNA, and you have to check for codons. You might be looking at maybe, 20, 30. But in our particular case, though, I'll just put this back on the screen here, it's just one line. And so that is really the magic of your code when you're working with Biopython. Now, let me just do something else here. I'd like to do let's do a comparison here. And what I want to do now is I would like to compare my DNA sequences here. I'm not going to do anything interesting here, but I just basically want to print them out to the screen. And then I want to have some kind of if they're different, maybe have something written so I can see that they're different. And so how I would do that is I have to write a for loop. That means I need to iterate through, hang on, let's write this out here. For I in range, I'll explain what I'm doing here in a second here, length something. So what I'm going to do now is I'm going to say, for I, this is my index. Now, remember that every string, as we discussed, every string is a character, made up of characters. And each character has a place. There's the first character, the second, the third, the fourth, the fifth, and so on and so forth. And so really I can give a number to the string, and I can say, give me the first character in that string, the second character, third, and fourth. And so what I'm going to do is I'm just going to go, we can do the other sequences later. But I'm just going to go through my DNA sequences now, but the other sequences are exactly the same. I'm going to go through this sequence of DNA, and I want to be able to kind of I want to be able to kind of iterate through that DNA here. So I'll just show you what I can do first of all here. If I go ahead and print this, and I put this little thing at the end here, this square bracket with an I in there, this is going to, I'll put a little thing here. Outputs the sequence char by character. So we have an idea of what's going on here. This is going to be basically putting up my characters or my sequences character by character. Hopefully we get this thing done today, otherwise we may have to come back to it. But I just want to show you what this thing looks like. If I go ahead and just save this, I'll come back to it in a second, everybody. Oops, oh, length, you know what I didn't do? This length I'm going to be saying, give me the length of my seq A. That means basically it says for I, or for one in the length of this sequence here, which is if this sequence has 10 characters, then what this lang over here it says is 10. It says the length of the sequence is 10, so therefore for I in range, and so 10, and for I in range 10, that just means count through from 0 to 9, basically. That's really all that there is. I think it's to 9. Yeah, it's because it starts at 0. So if I go ahead and run this, you'll see that here's my sequence. T-A-C-A. Well, that sequence is my first piece of DNA over here. It's this one here. I'm just not printing everything out as a one big string, but I'm printing everything out on its own line, and I'm going character by character. So let's go back to this again, and what I'm going to do now is I'm going to say, let's put a tab in there, just to make everything look kind of nice here. If I put that tab in there like this, which is just a quote, /t quote and comma, we've been doing this all day. If I go ahead and run this, you'll see now that everything's kind of like moved over. Now, what I'm going to do now is, and I'm going to be also printing out the, let's have on the other line here, I want to print out the other sequence here. So I'll just copy this. There we go. And I'm going to put out the other sequence right next to it. This is going to, the output's going to look crazy, and I do apologize for making it seem so difficult, but I think it should be working okay. Actually, one thing I could try though, well, let's go ahead and print this and run it. I've just changed the sequence here. Oops. Did that again. Running up. Let's put everything line by line. It's hard to see what's going on here. I think if I put a comma there, does that make any difference? No, it doesn't. Sometimes it would. Tell you what. Maybe if I do that, does that make any difference? I'll talk about that. No, it's the same. On some versions of Python, you can do that. But basically what it's doing is it's just basically saying, okay, here's the range, and then I'm just giving you the sequences for each of these things here. Now, what I would like to do is, maybe I don't want to go through all, I don't want to print all this stuff out now, but what I'm going to go through each of my sequences, and you know what, we're out of time now. I think I don't want to keep everybody here. Tell you what, can we come back to this on Wednesday, and we'll finish it up then, and then we have some other things to do on that day.